can be modeled in Abacus Explicit using explicit integration scheme. Also, blood flow and vessel deformation due to pulsatile nature of flow can be modeled through CFD and multiphysics capabilities. And lastly, for complex simulations, Abacus also provides us to couple our CFD simulation performed in other CFD codes to the structural simulation performed in Abacus. Secondly, Abacus provides us with large material model selection. Some particular ones of interest for us are superelastic plastic modeling capability of shape memory or nitinol alloy, a general hyperelastic modeling capability to model polymers and rubber components in our delivery system, an isotropic hyperelastic model to model vessel and other tissues, and viscoelastic model to determine creep and relaxation behavior. Accurate material model helps in improving the quality of our results. General meshing and element selection allows for economic solutions without compromising accuracy. For example, we can model guide wires with beams, delivery tubes with cylindrical shells, and stand struts with solid elements to reduce runtime but still obtain accurate results. In some cases, axisymmetric elements can be used to model axisymmetric geometries and loading. In addition, connector elements which connect two nodes in the model help with modeling of mechanisms like hinges and sliders. Our delivery system consists of multiple components interacting with each other through contact and interference fit. Also, when the stents are trimmed in delivery catheter, they undergo complex strut-to-strut and strut-to-graft interaction. This can be modeled through general contact capability as mentioned by John, which defines a single contact domain, and any component can come in contact with the other one in that domain. In addition, certain regions in the model which are much stiffer than others could be modeled as rigid bodies to reduce computational time. Finally, and most importantly, we like to use Abacus for its accuracy, speed, and flexibility. Abacus is designed to comply with ISO standards and follow strict quality monitoring procedure outlined in its website. This allows us to use various capabilities of Abacus as is for regulatory submission and approval. Abacus is designed to be scalable at all the component levels, so we typically run our models on 4 to 8 CPUs and even more to reduce runtime. In our R&D environment, we use both Windows and Linux operating systems. And again, Abacus allows model creation, execution, and post-processing on these operating systems at both 32 and 64-bit processing, allowing larger memory use. In a typical R&D environment, we run similar models with minor changes, and in that respect, Abacus allows us for customization of its graphical, pre-processing, and post-processing interface through scripting. This helps in creating and post-processing similar models very fast. We also use user subroutine capabilities to add certain features which are not available. For example, switching loading direction in the analysis based on stress response, customizing nitinol plasticity behavior, and so on. It is difficult to put a number, but I would definitely say that computer modeling and various capabilities of Abacus have helped us in significantly reducing the prototype time and getting regulatory approval in a timely manner so that we can get improved products to market and serve our patients better. On to the next slide, please. In this slide, I'll present a couple of examples. The first one is a model of delivery system inserted through the vessel. The goal of this analysis was to determine stresses in the delivery system as well as vessel walls when delivery system is inserted through tortuous vessel. This simulation demonstrated that the delivery system is stiff enough to strengthen the anatomy, thus reducing the chance of high stresses and permanent deformations in the delivery system components. We ran the analysis both in Abacus Standard and Explicit, and after seeing that Explicit had enough solution accuracy, we chose it for running other analyses based on its speed. Complex contact was used, and anisotropic hyperelastic properties for the vessel were also used. In the second example, we do crimping of stand with graft material inside a delivery catheter. This simulation gave us information on how far we can crimp the stand graft while keeping the strains in the stand within permissible limits. It also helped us in determining critical stress regions which we should optimize during design process. Again, this analysis was run in Explicit to model instabilities and enfolding in the graft material, and also contact between all the components. In addition, nitinol material properties or superelastic material properties were used for the stent. So we use Abacus quite extensively, and with this I end my presentation. Thank you again for your attention, and I turn it back to Howie.
Well done, Atul and John. Thank you again for enlightening all of us on these great capabilities. I'm sure our attendees will want to learn more about Simulia Abacus and the SolidWorks Associative Interface. If so, you'll certainly enjoy our technical demonstration.
In this demonstration of the associative interface, I will simulate the expansion of a cardiovascular stent into an artery. The stent is made of a material called nitinol. Nitinol is a complex superelastic material whose properties make it an attractive material for medical devices. Because it is a difficult material to process, simulation can be a particularly valuable and time-saving step in the design process. By taking advantage of symmetry, I can model a portion of the assembly in Abacus, and the results will be the same as if the entire stent were analyzed. Some of the modeling challenges associated with modeling stents and other medical devices include large deformations, contact between flexible bodies, and complex behavior of materials, both the biological materials and materials such as nitinol that are used to create medical devices. Here I have Abacus CAE and SolidWorks running simultaneously. In SolidWorks, you can see that I have already cut the geometry so that the assembly only includes the portion of the stent, the artery, and the balloon that I will be analyzing with Abacus. In Abacus CAE, I will activate the CAD interface that will enable Abacus CAE and SolidWorks to communicate. Now that the CAD connection is enabled, I will switch back to SolidWorks and export the stent assembly to Abacus CAE. The Abacus menu I used to perform the export was created by a SolidWorks add-in, which is available for download from the Simulia website. After the export, the association between the stent assembly in Abacus CAE and the stent assembly in SolidWorks will be maintained, so that the design modifications can be made in SolidWorks and exported into Abacus without losing analysis features associated with the assembly in Abacus CAE. Now, I will mesh the stent part in Abacus CAE. I will begin by assigning mesh seeds, which will control the size of the elements generated for the part. Then, I will mesh the part with brick elements. Brick elements, also known as hexahedral or hex elements, are the best element choice for this problem because they provide the best solution in the shortest amount of computer time. Generating brick element meshes can be challenging. However, the mesh generation technology included in Abacus CAE can create high-quality brick meshes even on relatively complex geometries, such as this one, with little or no user intervention. I will open the Element Type dialog box so you can get an idea of how rich the Abaqus element library is. While the default element formulation is appropriate for many structural applications, element